For our learning target here, you're going to be able to calculate the derivative of logarithmic functions, both the natural log or any other kind of common or uncommon base. Picture here is based on the calculus definition of a natural log. And the calculus definition of the natural log has to do with finding the area of, well, as you can see right here, logs underneath the curve y equals 1 over t. And we'll see what that's all about whenever we study integrals and antiderivatives. But until then, we need to focus on the algebraic definition of the natural log of x. So the algebraic definition is based on an exponential. Y is equal to the natural log of x. There is the logarithmic form of this exponential equation. E to the y is equal to x. Again, the purple one, that's the logarithmic form, and the green one here is the exponential form. All a logarithm is an exponent. You can see that the natural log of x is equal to y, and y is the exponent that you have to raise e to in order to get x back. All right, and then of course we can see our graph over here, the natural log. We've been looking at it for forever, okay? It is also the, let's say the inverse, yes, of an exponential. Here is the equivalent form of this natural log. In order to find its inverse, I take that y and that x and I switch places with it, and I get y is equal to e to the x, which is this function here, of course. All right, now, one of the things that I should definitely point out here is the domain of this thing. The domain of this is always x is greater than 0. Can't be negative. It can't be actually equal to 0. You have yourself a vertical asymptote there, of course. And then right here at 1, the natural log of 1 is equal to 0. The natural log of e, which is someplace right over here, that one is equal to 1, of course. And notice that this function is always, no matter what, going from left to right, it's always increasing. Now, since logarithms are inverses of exponentials, they're also exponentials in disguise, we can use the techniques that we learned in the previous lesson in order to come up with a derivative rule for the natural log of x. And that's what we're going to do right here. Find the derivative y is equal to the natural log of x using implicit differentiation on e to the y is equal to x, right? We just said that those two things are equivalent to each other. So let's use some implicit differentiation in order to find the derivative. Why do I have to use implicit differentiation? Because I have e to the y. I have a function with a y in the inside of it. Okay, here, let me scroll down here a little bit, make you dizzy a little bit. And, you know, I can start actually with the function that they gave us here, y is equal to the natural log of x. And then I think, oh, I don't actually have a derivative rule for the natural log, but I do have one for exponentials. So what I do is the inverse of both sides. I exponentiate. These are going to become the exponents on the base of e. Okay, and then e to the y is what I'm left with on the left-hand side, e to the y. And then these things are inverses of each other, so they cancel each other out, and it just gives me x back. Of course, this is exactly what we said that it was equivalent to. Now then, if I wanted to find the inverse of this, I would actually have to switch the x and the y coordinate. But I don't want to do that. I want to, at this point, just find the derivative with respect to x on both sides of this, implicitly. On the left-hand side, when I take the derivative of e to the stuff, it's equal to e to the stuff. That stuff. But then we have to apply the chain rule to this. And what's the derivative of y? Oh, we'll just call it dy dx. That should be equal to the derivative of x, which is just 1. And then finally, let's solve this thing for dy dx by dividing e to the y over here. So dy dx is equal to 1 over e to the y. Hey, what's e to the y? We just said right here that e to the y is equal to x. So this is equal to 1 over x. All of this means that the derivative with respect to x of the natural log of x is equal to 1 over x. Now, let me call your attention to again, the picture that we started this with, this objective, and that's 1 over t, 1 over x is the same thing with a change of variable, right? Right, and we're going to put those two pieces together whenever we start talking about how to find the area underneath the curve with some calculus. Okay, let's point out something about the domain of this function, though. So as far as the natural log goes, the domain x is greater than 0, right? And the reason why is because the domain and the range of these two things flip, of course, and the range of the exponential function is everything greater than 0. All right, now whenever I take a look at the function for the derivative, it's 1 over x. If you just saw that function, if you saw that function all by itself, you'd go, hey, the domain of this thing is all real numbers, not 0. It includes the negative numbers. But your derivative is not going to generate new x values from the original function. Remember, this is supposed to give you the slope at every single one of these points. So if the original function is not defined for some values, neither will its derivative. So that means, of course, that the derivative should have the same domain. In this case, x is greater than 0. Okay, let's come back over here and make this thing look real nice and pretty. The derivative of the natural log of x, let u be a differentiable function of x. So here's the derivative rule that we just derived. The natural log, or the derivative with respect to x of the natural log x, is just simply 1 over x, where x is greater than 0. All right, and then we apply the chain rule to this, saying that we're taking the derivative with respect to x of, oh yeah, there's the function right there. The derivative with respect to x of the natural log of u, where u is a function of x. So I take the derivative of the natural log of u as 1 over u, and now you have to multiply it times the derivative of the interior, which is du over dx, or just simply u prime over u. All right, it'll be a very, very useful derivative rule that we'll see that we will use throughout this lesson and throughout the rest of the year. All right, if I take a look at the graph here, the purple one is supposed to be the natural log, and then the green one, just like in the opening picture here, that's the derivative, that's the 1 over x.